Hello, everyone. I'm Stéphane Lafortune, a faculty member in the Electrical and Computer Engineering Division in the EECS department. And today we are visiting with Professor Steve Forrest, who is also a faculty member in EECS, as well as in Physics and Material Science and Engineering. Professor Forrest obtained his PhD from Michigan in physics, and after his PhD, he worked at Bell Labs, USC, Princeton, and returned to U of M in 2006. Professor Forrest has received numerous prestigious awards and professional distinctions in his career. Notably, he is a fellow of 3 professional societies, and he is a member of the National Academy of Engineering, as well as other national academies. At Michigan, he is a distinguished university professor, which is the highest distinction that the university bestows on a faculty member. Steve, it's a pleasure to be with you in your office today. And we thank you very much for taking the time to answer our questions and talk to us. I am joined by Lydia Fraz and Felix Sun, who are undergraduate students in the College of Engineering with an interest in sustainability. So we would like to touch upon 3 topics in this conversation today. Carbon neutrality at the University of Michigan is the first topic. Then we would like to talk about your research activities in organic electronics and beyond, and their application to renewable energy. And on a personal note, we would like to talk also about what it is like to own a house that is off-grid. So we can start now with talking about carbon neutrality at the University of Michigan. Professor Forrest was the co-chair of the U of M Presidential Commission on Carbon Neutrality. The other co-chair was Professor Jennifer Haverkamp of the Graham Institute for Sustainability. They submitted their report in 2021, and now the university is proceeding with the implementation of their recommendations. And I would like to ask Lydia to start with the first question.
Thank you. So, Professor Forrest, after working on the President's Commission on Carbon Neutrality as a co-chair, what are the greatest takeaways that you had from your work? And how do you think the university is doing implementing those and those greatest ones, as so many were passed?
Yes, well, thanks very much for asking the question. Thanks very much for inviting me. This is a really important issue. It's the issue of our time. We worked for 2 years. It was a very interdisciplinary commission. I'm obviously an engineer, but there were people from the city, from the social sciences and humanities. There were people from the School of the Environment and Sustainability. So we had a really broad constituency. I think what this was just an extraordinary learning experience for all of us. We had a lot to learn from each other. You know, as an engineer, I know how to fix things. I know what a wrench does and how to turn it. But when you talk about things as gigantic as changing our basic infrastructure of this country, of the world, to meet the needs of coming to a much more carbon neutral environment, it's not just about fixing things, it's about getting people to work together. We need everybody to work together. And I think probably the biggest takeaway is just how enormous the problem is. And even in the time since we submitted our report till the present, it's become an even more urgent issue. We are no longer in a situation where we can just sit back and do things when we get to them. This is a climate emergency. There's no question about it. So even our goals, I believe, are, in light of what we have come to know in the more recent past, are just not urgent enough. But I can say we did come up with a viable plan, again, about 65 recommendations that will bring the university to a carbon neutral point in a very sustainable and just way. And part of this, and the human aspect, again, as an engineer, you don't initially or immediately think of this, but the whole issue of getting to a carbon neutral future has a lot to do with social justice. It's sometimes called environmental justice because disadvantaged communities have been also disadvantaged in the burden that they have to shoulder because of the energy choices that we have made over the decades and centuries. And then you go then to other, not just in the US, but now you go to other countries around the world and you can see the struggle of the developing countries versus the developed countries. The developed countries have taken advantage of an energy system where energy was very inexpensive, and we built our infrastructure based on that inexpensive energy, and we benefited hugely economically and our standard of living. And now other countries won't have that opportunity, but they will be very much impacted by our choices. For example, flooding in countries like coastal regions of Bangladesh and so on are paying the price for what the rest of the world, or the developed world, has taken advantage of. So we have to figure out a way to get into a future where everybody can participate and gain equal value. And so the whole business of social justice became very central to our commission. This was very unexpected, right? You asked me what I learned. I went in there thinking, well, let's just do a lot of solar and wind, make some batteries, and problem solved, because the technology is there, right? We have the technology, and the technology is very inexpensive, but that's just the first part of the problem. And now it looks like we're going to have to clean up the atmosphere too, and do a lot of mitigation by extracting carbon dioxide, removing the damage that has already been done. So this was really quite a process. It was as much political as technological. I think that's the way to say it.
All right, thank you. Yeah, that's really nice to hear your thoughts on that, and a lot of the things that when you continue researching, it's interesting to see how much it kind of affects third world countries or countries who might not have been at the peak when development was occurring.
And even our own country.
Yeah.
Right? I mean, if you look at the communities that are really disadvantaged by our energy choices, they tend to be very low income, or the lower part of the income scale, because that's where the polluting plants have been put. Right? Or maybe those communities moved in around those plants because they had reduced the value of that region, right? Mm-hmm. So these people are breathing a lot of the smoke that the rest of us just get the electrons coming down the wire from, and we don't know what the penalty or the cost is from that. Mm-hmm. So if you look even in this country, I mean, the US it's not really a microcosm, but you can think of it as an example of what's happening all over the world, because we have that distribution of wealth and distribution of energy sources. I mean, we're really a blessed country. We have places where the sun never stops shining, and we have also places where the water never runs. So all of these things are things that we have to take into consideration here.
Thank you. So with that report then, keeping those thoughts in mind, what would you say the greatest recommendations, kind of with that whole interdisciplinary aspect between the social environmental justice and then the engineering aspect, that have been implemented on this campus?
Let me do one thing to answer that question, or let me just dive down a little bit and just take us down one level about what sort of considerations we go through. So the first thing I want to talk about is, what is carbon neutrality? I think everybody has to understand that. So these are all sort of texts that were developed by the commission after a lot of thought by a lot of smart people. But as it says, at a global level, carbon neutrality means having a balance between how much we emit in our everyday lives and in our businesses. And we want to have a balance between the carbon that we generate and what we absorb from the atmosphere in carbon sinks. So the best solution to this, of course, is to emit as little as possible. Absorbing is pretty hard. So at the level of an institution, and you have to remember that U of M is 3 campuses, and we have to keep that very much in mind, and they're very diverse. Our own 3 campuses are extremely diverse. We have the Ann Arbor campus, which basically spreads out all over the city of Ann Arbor. And it's not a tiny city, but it's a mid-sized city. But it is the University of Michigan in large degree. Then we have the Dearborn campus, and that is sitting in a major suburb of Detroit, a much bigger city. And the people who go to the Dearborn campus are commuters. So if you are in the city of Ann Arbor, the students live basically on or just adjacent to the campus. Everybody's within walking distance, a huge proportion.
Sure.
Right? So now we have a commuter campus. And by the way, most of the workers who come to Ann Arbor and work on this campus, the tens of thousands of people, and the hospital staff and so on, they're very often commuters as well, because the prices in Ann Arbor are quite intense. Okay. And then we have Flint, which is a sort of legacy manufacturing community, trying to retool itself, to use something of a pun, to become more adaptable to the new economic reality of that region. So it's actually, of the regions, it's the lowest income of. So now we have, and there, by the way, the size of and scale of these campuses is also vastly different. Flint being the smallest, Dearborn being mid-sized, and then of course Ann Arbor. So we had to take all of this into consideration. All of them have very different carbon emitting challenges because if people are commuting. They are also spending a lot of carbon getting there. And, the wealth of the communities makes a difference too. So now the next stage is we have to be able to solve a problem. This is something that every engineer understands. To solve a problem, you have to be able to measure what you're doing. So we have to quantify our greenhouse gas emissions. And not all greenhouse gases are created equally. Okay. We have carbon dioxide, which has a certain greenhouse intensity. And then you have methane and propane, which have a much greater carbon intensity. So it's about 30 times higher than carbon dioxide. And then to get into sort of an accounting balance between emission and absorption, we have to figure out how to use less, produce cleaner energy, and that which we cannot do, we have to offset by investments in projects that globally reduce carbon. So it's we all live under the same tent called our atmosphere. And so if we eliminate it in one place, we can afford to emit more in another place. Although I don't think we can afford to emit any more than we do. So then if you break it down, there are 3 scopes of emission. Scope 1 is what we create ourselves. And if you go to the corner of Washtenaw and Huron, you'll see a huge power plant.
Right.
That's a natural gas power plant, and that's for heating and electricity. We have, I believe, 3 power plants. There's another one up on Huron Parkway, NCRC. And so that's creating carbon emissions. That's a scope 1. Scope 2 is purchased electricity. So that's what comes in from the wires in this campus from DTE. On the other campuses, or certainly from Flint, is consumers. And that one actually turns out to be the easiest one to fix. and the cheapest, and that's being fixed right now. And then scope 3, this is a head scratcher, because this is everything else. So, for example, we're sitting here with our computers on our table. There's a certain amount of embodied carbon in all these things. They were manufactured, well, probably part of it in China, part of it in Korea, another part of it, an assembly was done in the United States, maybe, who knows? Okay, but each one of those things, and these parts were shipped everywhere, there's carbon intensity there. So that's called a scope 3. The commission decided all scopes were open season.
Okay.
In other words, the food that you put on your table is a scope 3 emission. Farmers emit carbon. We wanted to get it all right. So this was very, very ambitious. Not getting too deep into this, but it's important as engineers to recognize that we have to measure something. So in the vertical axis here is our ability to confidently estimate the emission levels, and the horizontal is how much we can do about it, right? And so you start with the easy pickings, something you can easily measure and easily fix. And it turns out that's scope 1 and scope 2. So just to give you, I know this is a very windy answer, but to give you one example, scope 1, we're getting all of this energy from our power plants on campus, and they're big carbon belchers, right? How are we going to solve that problem? Some of the buildings on this campus are over 100 years old. Some are brand new. Mm-hmm. So there's a whole range. And for that, there's actually only one practical solution, and that is geothermal energy. Nice. To convert the campus to geothermal energy would take about, I think the number is 2040 to get it completely carbon neutral in that respect. You'd have to convert the heating and cooling and electricity system of every single building. So it would take 20 years, and it would take $2 billion. Now you think $2 billion, where does that come from? Well, we were very concerned that it would, of course, all come from student tuition, and then now you're back into carbon justice, or to environmental justice, right? Because who's going to pay the brunt of that is going to be the students who are most disadvantaged from an income perspective, okay? So we worked all that out. Actually, $2 billion is not that much money. Over 20 years, that's $100 million a year, and we spend more than $150 million every year on physical plants at this university alone, this campus. By the way, this is for all 3 campuses.
Okay.
And geothermal is changing. It will get cheaper with time. So in 20 years, it'll be much more popular. It'll be going in much faster. The Department of Energy is working on making it more accessible. So I think it's very reasonable. But when you first look at that, the size of that bill, what would any administrator want to do but fall over in a faint, I suppose? But then you realize there's plenty of on-ramps and off-ramps here. There will be other technologies that might come in the meantime. So things are moving very, very fast. And the university took all of this on. The only thing they didn't completely endorse, they took it under advisement, is the issue of carbon offsets, of paying for projects that don't directly impact the university itself, but for example, setting up a solar plant in southern Mexico or something like that. You have to be very, very careful with carbon offsets because some of them are bad. They're not really they're oversold, and they're not actually creating a reduction in carbon. And a lot of them also, again, disadvantage people who are very vulnerable. And they put in a plant where, run people out of their homes, indigenous people, things like that. So you have to be very, very careful. But let's face it, if you you as a student, you go home or you go on vacation, you get into an airplane, that airplane's going to run on fossil fuel for any for the foreseeable future. How are you going to pay for that in a carbon economy? And that you're going to have to do offsets at some level, and everybody understands that. But I'm very happy to say the university took all of these recommendations and endorsed them, and the target is to get to carbon neutrality at 2040.
You talked about geothermal. How about solar energy on campus or in the
Solar
vicinity of
energy is
campuses?
very, very important. As a matter of fact, that and wind are the primary opportunities in scope 2,
Okay.
and that's already in motion. I know that at the time of this writing, we had purchased, President Schlissel had purchased about 50% of our external energy from renewable sources, and now they have a request for proposals out for the other 50%. It's about, I think it's 75 megawatts of power. So that would be solar. I have read recently that, and this was one of the things we talked about on our commission, is when we bought the Pfizer property, which is now North Campus Research Complex, there's 150 acres sitting right across Huron Parkway, which has nothing but weeds on it and an automated automobile test track.
True.
And so there's still a tremendous amount of space there for solar. So we can build our own, but it would probably be built by the local utility like DTE, but that's space that could certainly be used. So geothermal requires solar because you need electricity. So it plumbs a lot of energy from the earth. The way geothermal works is in the winter down underneath the earth, it's warm. And in the summer, it is cold because it's the mean temperature of the year. And so you can get heating and cooling from it.
Okay.
It is a massive project for this campus alone. You need, as I recall, something like 30,000 boreholes. It would be the biggest geothermal project on the planet today. And you've got to find space for those boreholes. Well, there's that fallow land, but there's a lot of piping and everything else. You have to worry about getting across rivers, which we have crossing right in our. It's very complicated. At any rate, we had a consultant firm rough out the project for us and gave us the price and the schedule and so on. It's definitely doable. It is definitely doable. It's just a matter of will, and I think the region certainly endorsed this entire proposal. So, and we're starting already. The new building that you see behind the computer science building up in that once it was a parking lot, that is going to be geothermal.
Right.
There are a lot of ways this can be done in a scheduled fashion that doesn't disrupt all of the activity on campus. But we have these con buildings in Central Campus, these beautiful brick constructions, like Randall Lab, Hill Auditorium. They have very old systems, and we're going to have to completely redo that. And this is going to take a lot of cash and a lot of disruptions. But we'll see. I think the only thing I probably regret is 2040 seems too far off for me. I think it should be 2035. So, but things are moving at least.
So Professor Forrest, just as one kind of final follow-up, as a student who's involved in a lot of sustainability organizations on campus, what would you say as students here at the university, what are the biggest and most impactful things we can do to get involved, especially with this commission being so recent?
Well, first of all, I think that none of this would have happened without student activism, right? It was students who made this a demand. It became a non-negotiable demand in the end, and for very, very good reasons, because the students today are going to be the most impacted, right? The young people. So activism is definitely something that is needed and must be sustained. It doesn't always have to be frantic and extreme, but it has to be constant. And like I said, this whole carbon neutrality movement on campus and the response of the administration would have never occurred without constant pressure by the students. So, believe it or not, the students run this place, and as it should be. Now, the other part of that question is what should you do? And I know everybody feels that, well, if I turn off the light in my room, it's a drop in the ocean. And it is a drop in the ocean, but the ocean is comprised of right now 7.5 billion drops. So everything that we do makes a difference, whether you walk to work rather than take a car, take a bus perhaps is a better solution if you're living a little bit further away. What food you eat is crucial. Beef and lamb are the most carbon intensive forms of food that we can have. So putting more vegetables in your diet, these little things actually are extremely important. You need to be aware, as I am, in every action we take when I get in a plane, I always feel guilty. I know I have to get in a plane, right? Because that is part of what I do. But I'm aware of it, so I know I'm going to fix it. My automobile, I now drive an EV. I've been moving in that direction for a long time. I had a hybrid, and I said, no, that's not good enough. I'm going to get an EV. I'm very, very intense about when I go down to Pierpont, for example, making sure that I'm putting the right stuff in the right bins for composting and recycling. This is extremely important that every one of us do this. And I think that students really are rather slow at coming around to how important that stuff is, because they think, I'm busy. It's not really big in my field of view. Yes, it's big in your field of view. You have to make it so. So being an activist is one thing, but you should be an activist in your own life too. And I feel I need to lead by example, but I think so do you.
Thank you so much. That's very inspiring and great to think about.
Thank you. So our second topic in our conversation with Professor Steve Forrest is to discuss his research program and its applications to renewable energy. And I would like to ask Felix to ask the first question.
So this semester, I'm actually taking Engineering 100, Section 420, which kind of focuses on an introduction to solar cells. And so considering this, could you explain the basis of your research to someone like me who has a basic understanding of solar cells and an introductory level of that?
Sure, glad to. Thanks for the question. Well, I've been working in solar cells for most of my adult life, among other topics, but it's really a fascinating one. There's a fabulous amount of energy that comes from the sun. I've got a little chart here that shows that on a sunny day in Michigan and most of the United States, we have about 1 kilowatt per square meter of solar energy. So this is the source. Actually, virtually all energy on the planet comes from the sun. No, I think I should amend that. All energy on the planet comes from the sun, including nuclear. It eventually got here as an accretion. Okay. So a kilowatt per square meter, what does that mean? So if you think about maybe a standard room has a roof of, let's just say 9 feet by 9 feet, that would be what? That's about 3 by 3, so that's about 10 square meters. So that's 10 kilowatts. The average household in America is probably running, on average, at around 2.5 kilowatts. So there's enough on one room of one roof, the roof of one room to power the entire house. Of course, the solar cell itself doesn't have 100% efficiency. So we have to take that into consideration. What this chart shows is the efficiencies that are out there. And silicon solar, as you probably can look around North Campus, you can see the large solar field that exists on North Campus Research Complex. Silicon is king, and the panels out there are probably about 20% efficient, which means 200 watts per square meter. Still a lot of energy, more than enough on any average rooftop to power everything. Turns out that solar is the cheapest form of energy that mankind has ever had since the Industrial Revolution. And that includes the cost of the panels and all the infrastructure that goes around it. But you asked the question of how they work, so I have this little cartoon, which basically says the sun is very generous. It gives us this magnificent amount of power. In 1954 at Bell Labs, the solar cell was invented, and the solar cell is basically a slab of semiconductor with a junction in it, and the photon is absorbed in the semiconductor, let's say silicon. There are other materials that I'll talk about in a minute, and that creates an electron, and that's part of where the efficiency comes into this thing, is how many electrons are generated for how many photons, right? That's what's called the quantum efficiency. But what's more important is the power efficiency. How much power does this thing output in this electric current that's generated per incident photon? And that's where the 20% or 200 watts per square meter come in. So it basically, photon comes in, creates an electron-hole pair, because remember, a photon has no charge, right? So what it generates can have no charge. So it creates an electron in a semiconductor and its positive countercharge called a hole. And they get separated by the internal field at the junction and are extracted at the contacts. So that's the basic operation of a solar cell. And when we do that, we come to these sorts of solar fields. And right now they're unsubsidized. They are cheaper by at least a factor of 2 on most areas of the country than fossil fuel, which is subsidized. So the unsubsidized cost of solar is a factor of 2 cheaper than the subsidized cost of fossil fuel. And there are vast economic supports for the fossil fuel industry, which nobody talks about, but it's there. So we as taxpayers are paying essentially to poison ourselves when we have all of this free energy coming from the sun. So the question is, how do we use it? And of course, the first objection comes, well, the sun goes down at night. And by the way, wind is also very, very inexpensive, probably just a little bit higher than solar today. It used to be the cheapest, but solar got better. And the wind drops every once in a while. So what do we do then? Well, we need battery storage. And there's many different forms of battery storage. But that too is moving along quite rapidly. The most efficient form of battery storage is lithium-ion batteries. And Michigan itself is creating a substantial industry in battery technology. It seems to be where we've put our stake in the ground. There's a lot of competition between storage for energy distribution to homes, etc., and the fact that lithium ion is also great for electric vehicles. So these are just technological problems. And again, as an engineer, I think if it's technology, we know how to solve it. Economics has to follow technology, or maybe even precede it, but there's no longer an economic barrier to replace fossil fuel with solar. But to build a project like I have on this photograph, that takes a lot of financing and that sort of thing. Those are details as far as I'm concerned. So those are that's how solar works. If you want me to go on, I can tell you a little bit about my research.
Yep, that sounds good.
So this is silicon. It's great. And it's the king because it's cheap. But in my little chart, I also showed some other technologies. And I like to work on this one at the bottom, organic solar cells, and they seem to be the least efficient of all of them, but they're really interesting. So what do I mean by organics? So organic materials are all around us. Our clothing, our dye, have organic dyes in them. Most of those organic dyes are semiconductors. And we know that dyes are very cheap. Otherwise, our clothing would be very expensive. Also, paints have organic dyes. An organic molecule is one that is, there are more formal definitions, but for the purposes of this discussion, they are carbon-containing compounds. And they're highly colored, which is why we use them for dyes, photographs, everything else. And they come in sort of three types: monomers, which are self-contained molecules. They have a well-defined molecular weight. You can string monomers together and form polymers. Those are plastics, tough, flexible, etc. Both monomers and polymers make good semiconductors. And then biological molecules, the stuff we're made out of. Those are also organic materials. And but those are very complicated, as you can obviously see, just from looking at the diagram. That's a protein structure, etc. We don't know how to make those things, but they're really effective solar cells. They're called plants. And so nature for 2 billion years, maybe more, has been working out how to optimize photosynthesis. And it's just another form of solar cell. It actually does something very close to what my solar cells do, which is creates an excited state in a molecule. It transports it somewhere to another molecule, that excited state, and then it generates an electron and hole. It separates into an electron and hole pair, and that's in the leaf. It's doing exactly what our solar cells do, except there it takes the electron and changes starch molecules to sugar molecules, right? And that's what a plant does. It converts electrical energy to chemical energy. We take electrical energy and we keep it in its electrical form. But I like to say, if you're competing with silicon, go home, you've already lost. I think this is what any electrical engineer will say to you in some form or other. So what do we do that's different? And why should we care about organics? They make large area things. This display I have behind me is an organic LED display. So it's large area. They're low cost because they go into our clothing. They're flexible because they can be on plastic. They're conformable. That means they're shapeable. They're easy to manufacture. Well, we know that from all these color industries. And they're ubiquitous. Okay, so what can we do with them? So this is something out of our lab. You might recognize the scene. It's sitting between, I guess, EECS and what, Gigi Brown, is it?
Dow building.
Dow, that's right, Dow. And we make solar cells that have different colors to them because these are colored materials. But we can also make them quite transparent. Not only can they be transparent, they can be very, very efficient because there's a lot of the energy that comes from the sun that's in the infrared that we don't see. So we can make windows now that are very appealing, attractive, not colored. We don't want to have these deeply colored windows. It's like living behind an optical filter. You want it to be more or less neutral density. Actually, we like green tint, it turns out. Just a slight green tint is what the windows are in your house. You never know it's green tint. All right, little detail. You learn it when all these things happen. But we can make a solar cell that's about, well, you can see 10% efficient, 100 watts per square meter, but is also 50% transparent. So why can't we put these on all our houses? In some buildings, like the Hancock Building in Boston, is just one curtain, just 4 curtain walls of windows. They could all be generating a huge amount of power. In your house, a few windows on the south-facing side, and you've pretty much done the job. So that's one of the applications. And then, University of Michigan is not a land-grant college, so we don't have an agriculture school. But we do have a campus farm. We have Mathai Botanical Gardens. You've been up there. Mm-hmm. Have you? You should be. But they have a campus farm, and some of the food in the residence halls comes from the campus farms. Okay. So I'm thinking, well, we can make transparent panels for windows, which is kind of the fat part of what we're doing. We can also use transparent panels to use in fields, in agricultural environments. So, for example, in Germany went really big about 15, 20 years ago into solar. They thought they'd get rid of all their nuclear, which they did. And now we have the Ukraine war, and they're struggling because of the choice they might have made too early. But what happened is that the farmers in Germany realized that they could make probably more money as a public utility selling electricity with solar than in growing their crops. And so they ended up dominating too much of their land with solar. And by the way, you can go out into Germany. Some of my family lives in southern Germany, and we go on walks all the time through the countryside, and every barn is covered with solar cells. I mean, everybody has them. A huge barn roofs. It's really something to see. But you go on the Autobahn, and the fields themselves are really covered with solar. And so they started to lose too much agricultural land. So we thought, why can't we all just live together? And why can't we use these transparent solar cells to feed the plants and at the same time generate electricity? Turns out plants need mostly blue and red light. They don't need green, so we can use that for power generation, and they don't need infrared. And this is one of our little panels just showing on, again, North Campus with some vegetation behind it. So agriculture. The fact is that solar can go anywhere and do anything. It's really an extraordinary technology. And I love working in it. The scientific challenges, it's right down to quantum mechanics and understanding how electrons and how excited states transfer from molecule to molecule. So you right down at the quantum mechanical level all the way to the very practical level of making a panel. Now, I can't make a panel like this in my lab because so maybe I can keep a chia pet going, but we're working with the campus farms to demonstrate this type of technology.
Let me ask a question that I've heard people mention is, what is the lifetime of, let's say, a silicon solar panel, and what would be the lifetime of one of your transparent films?
Good question. So, and it's exactly the question that I'd love to answer because we work a lot in the lifetime of cells, and we're probably the world leading group of this in organics. So silicon cells are basically guaranteed for about 25 years of operational lifetime. Now, that is not really their lifetime. In some cases, it's shorter because they haven't been made well, and in some cases, it's considerably longer. But that's sort of what one would call the factory certification. Okay. We have been doing accelerated testing on our devices, and they are between 30 and 60 years lifetime. So we think about organics, right? I go back to here. Biological molecules, we're filled with that stuff, and we know we die. So we always think that the lifetime of electronics based on organics is just not sufficient, and that's just not true. It's a myth. This display would not be able to be sold if it didn't last for long enough for the consumer to use it. Of course, a display lifetime doesn't have to be like a solar panel. Sure. These double paned windows, which our solar cells would go into. So I've had a lot of discussion with the window industry. By the way, a lot of that is centered right here in southern Michigan. Guardian Glass, one of the biggest manufacturers in the world, is just 20 minutes or 40 minutes from here. These double pane windows are guaranteed, I think, something like 15 years before of course they last longer.
Sure.
But nobody wants to guarantee them for longer because then you have to replace them if they fail. Our cells sitting in those windows would not shorten the life of that window at all. They'd actually last longer than they're guaranteed for. Now, these are laboratory measurements of lifetime. Putting them out in the field is always going to be a bit different, and we're working toward that. But I don't think that lifetime is a problem.
What about the infrastructure needed to connect these thin films
In your house.
in your house to?
So new constructions are easier, obviously, because that's
Okay.
when you're installing the windows. But to give you an idea, well, first of all, a solar cell puts out DC, not AC. Your house runs on AC, although there are circuits in new constructions that are DC because LED lights work a little bit better. But let's leave that aside. Let's assume everything is 120 volts AC. So we have done the cost analysis. So the panel itself, the window, would have to have what are called microinverters, little circuits that you put on the edge of the window. You wouldn't see them. They'd be behind the sash, that convert the DC to 120 volts AC. So the panel would have a certain amount of DC voltage, maybe 40 volts, and it would step it up to 120 volts and it'd be AC. Now you have AC coming out. Good. You have a plug. Okay. Now, if you've ever seen a new construction, your house is built exactly the same way. The Romex, that is the power lines that feed all these sockets, goes right under the windowsill, right? They're just a foot down. So all you have to do is hook that AC, 120 volts, right into your line, and you're done. Okay. Now, in new construction, of course, you just plan for it, and you do that all before you install the window. And in commercial buildings, of course, it's another challenge because these things are put into metal frames and so on. It's just a design problem. It is. We have looked at the cost. We've done what's called a techno-economic analysis of power generating windows. It turns out that the premium, how much more the window would cost, is about a factor of 50% higher. Without subsidy, there's a lot of buildings that are subsidized to go carbon neutral, particularly in Europe and Japan and some in the US, that it actually becomes free. The whole window becomes free because of the subsidies. But let's not go there. Let's do it without subsidies. Without subsidies, it would take between 2 and 6 years in a normal environment on a south or west facing window to pay itself back. So 2 years is not a lot of a window that lasts for 30 years. And that does not include installation cost, which would make the increment go down further. Installing a window costs as much as the window.
Yeah.
So it's a pretty good economic proposition. And so the Department of Energy is very interested in this. Let me just talk a little bit about what happens in a solar cell. So I like these cartoons. They're kind of cute. Like I said, the sun is extremely generous, but what happens microscopically in a solar cell, and this is an organic solar cell, is the photon goes in and we have this structure. It's only about 100 nanometers thick. The whole thing is really, really thin. So what's 100 nanometers? I guess a human hair is something like 20 to 40 microns across. So a nanometer is a thousandth of a micron. So this is about the hundredth of a thickness of a human hair, right? That's all these things are. And when the photon comes in, it creates a molecular excited state. That is, we're just exciting this molecule that I kind of showed you before up to a higher energy level, a new quantum state. And that new quantum state can hop from molecule to molecule to molecule in the solid. And that's transporting that excited state, which is shown by this kind of dashed line when the photon first comes in. Let me put my cursor here. It creates this excited state. Now it gets to a junction. That's the junction of the device. And that's kind of these interdigitated at the nanoscale structures that consist of two different organic materials. And when the exciton bumps into that, it splits up into a separate electron and hole. The electron is shown as the dark circle, the hole is the white circle, and it goes into the external circuit. And we have learned in our lab how to structure these interdigitated fingers. So I've taken the top off of this thing, or not put the top on yet. And you can see these little protrusions. Those are tiny crystallites on the order of 2 nanometers in diameter and 10 nanometers high. They're really teensy, really small. That's a technical term, teensy. And that's what you need to do. And you need to do it over areas, the size of the substrates that we put these on might be 2 meters by 2 meters. So it comes from the OLED display industry, which is also something we have worked on over the years. This is this display. It's a 55-inch display, and it's on a piece of glass which is 0.3 of a millimeter thick. Now think about that. So it's like paper. It's that thin. And that's how, and now the OLED layers, the organic layers for the organic LEDs that make this display are again 100 nanometers thick on top of that. So that's what we're talking about when we make these solar cells. And so it's all about nanostructuring. It's about manufacturing things on large area. This particular display, for example, was made on a piece of glass that was approximately 2 meters by 2 meters. And then the TVs are cleaved up into bits like this. And it's exactly the same technology that we would use for solar cells.
So where would these solar cells be made?
That's a good question. The displays today, the OLED display industry, which started here in this country, is now almost I'd say it's entirely made in Asia, primarily Korea. China is coming along. Japan does some of it. But these are large-scale commodities. And that means that the factories have little or no labor in them. And what labor exists has to be quite cheap. So that's why these things are made overseas. The largest solar cell company in the world today, I believe, is First Solar. And that's in Toledo, Ohio. That's its headquarters. It does a lot of manufacturing in Europe, and it does manufacturing in Asia as well. Okay. So these things are global industries now. So I think that this solar industry will have a real footprint in the U.S. Where and how, I don't know, but the silicon chip industry, the U.S. government has made it a strategic decision to bring the chip industry back into the U.S., or at least some of it back into the U.S. And we now have silicon fabs in the U.S. that are quite capable, but not quite at the capability of, for example, a TSMC in Taiwan. But all of these movements to get manufacturing back on shore, particularly for these critical and strategic technologies, is helping bring also things like solar back into this country. I am very skeptical we'll get displays back into this country. It wandered off in 1985 and has never looked back since then. And we lost the TV industry. So yes, I think that, and of course the Department of Energy is only interested in things that are manufactured in the US, and that becomes a criterion for winning a research grant from them, because they say, well, give us the manufacturing case for it being cited in the US. And for a professor, that's not always so easy, but we do our best. And I'm working with, I helped start a company that sells, it's based in New Jersey, and it sells all of these organic materials to the display industry globally, and they're also going to be manufacturing materials that have come out of our laboratory for the solar cell industry as well. So there'll be a big domestic footprint to this.
is there a difference between the rare metals that are needed for regular silicon-based solar cells versus your organic solar cells?
All the materials are different, except for one of the harder materials to get a hold of is indium tin oxide, which is the transparent contact which you see here. That comes from indium mining, which is really, indium comes as a tailing or as a byproduct of aluminum mining. And we have aluminum mines in the Dakotas and places like that. That's the most expensive and hardest material to get one's hands on of the raw materials that go into this. There are no rare earths in these materials at all. They're basically carbon, nitrogen, oxygen, pull them from the air. By the way, these things are nice carbon sequestration units, right? You're making, of course, you use a lot of carbon in making the carbon containing compounds, but everything costs something. But when you talk about a 2-year payback, that's also a carbon payback, right? Because you now use these energy generating sources that are renewable to make the next ones, right? Energy is energy. So as long as we're investing in solar, we're using solars for manufacturing too.
So for the last segment of our interview with Professor Steve Forrest, we will talk about the challenge of living off-grid. So Steve, I understand that several years ago you faced that challenge in your house in Vermont. Would you share your experience with us and tell us what you've learned from that?
Sure. For this, I'll actually use this little display here. So I used to live in New Jersey, and my family, my kids, and my wife and I would always go up to Vermont to go skiing or to do this and that. And finally, one year we decided, we go up there so often, let's buy a house. And I just found a house on the web. I sent it around to my kids. They said, oh, yeah, that's a great house. Let's go get it. And it was off-grid, and it had very little power. It had a propane generator sitting in the garage, and it had a switch in every room in the house that when this fellow who was living there, he was a hunter, so he's in the backwoods there, he'd roll out of bed and he'd turn the switch and on would come the generator, and he had a couple batteries out in the garage. And I was talking to him, and he says, well, I just go out and I measure the battery level, and when it gets to a certain, with my meter, and when it gets to a certain level, I turn on the generator. And I realized this was not going to work with my wife, who's not an engineer. So when we bought the house, which looks like this, that's when we first moved in. It's this kind of sprawling. It's got a barn on the left in that picture, and the garage is way on the right, just kind of out of the picture, and the rest is the house. And it wasn't in great shape, but it was a lot of fun. And there's a little map there, and it shows that the house exists right in the center of the state. I always like to think of Vermont as a trapezoid. And so to find the center of a trapezoid, every engineering student knows you draw a line between and that's where our house, the intersection point. And as soon as we bought the house, I went down to the local restaurant with my kids, and we drew out on napkins. We got to power this thing up with solar. And this was a long time ago. This is nearly 20 years ago now. There wasn't a lot of solar around. So we sketched out a system. I'm an electrical engineer. I know how to do these things right, I thought. And so then we had to go and find some solar panels. And this is kind of where the industry was at the time. We didn't buy them from here, but you kind of get the idea. It's kind of a backwoods effort for enthusiasts. Now you can really, it's a big business. But so we bought some panels, and we started to work on putting the thing together. We decided to put it on my roof. So I got my sons to working. They're my cheap labor. The tall guy, these are when they were quite a bit younger, I should say. 20 years ago. One of them is an architect and one of them is a chef. And they pitched in. This, by the way, over here is the generator. This is our garage. And we're going to put the batteries somewhere over to the right here. And we went to Home Depot, bought a whole bunch of stuff, raw materials, and we got the panels, okay? And that's my son with his wife, is another architect. And they're looking at our panels here. This is the back side. These are the frames we put on it for the roof. And of course, when you get two architects together, you just get discussion. I mean, oh, it shouldn't be this way. It should be this way, etc. This is so much fun because it was, I'm obviously very dedicated to solar, to carbon neutrality. So this was sort of a project of love for us. And it's also fun to do this with your kids. Okay, so we got them all, these stands all built. And now we take them up on the roof. They don't look terribly professional, but they worked pretty darn well for many years. I'll tell you what happened. So there's me on the roof here, handing it up to my son. And we had ropes. And this is where I didn't know much about Ohm's law, it turns out. So we put it way up on the roof, and I bought this really heavy copper cable because I didn't want to have any power loss getting down into the garage. And it was about 80 feet of copper cable, really heavy. It's still sitting in a coil in my garage. We took it all down. And those are the panels up there. And so that's how it looked. That was the first 4. So each of those panels, first of all, they cost about, I think about $6 per watt. They were about 100-watt panels. So you're looking at a lot of money there, right? That's about a few $100s per panel. Today they cost about retail about $1 per watt. So this would be, the whole thing would be about $400. This was then about 500 watts. So we were pretty energy starved for our house. It's up on a metal roof. We have a friend up there. He has since died. He's an old guy, an old Vermonter. And he loved to tell the people in town, which is about 6 miles away, Steve put his panels on the roof so they would be closer to the sun. The next thing he said is, doesn't he know that the sun shines just as bright on the ground? The real problem with putting them on the roof, of course, is that it snows in Vermont. It snows a great deal right now. Actually, this is now late March, and we have about 5 feet of snow on the ground in our house. So to get on this, to clean these panels, just to remind you what this house looks like, the panels are sitting up here, and I'd have to get on this roof with actually I used a broom and just leaned up over these dormers to clean them off. And then one day we got a new roof on our house that was much slicker. And I was up there during the rain or during the snow, and I slipped. And this is about 25 feet. And I grabbed onto the standing seams. It was the New England standing seam. And I had my fingers like this holding on. And I called to my wife, who was in the kitchen, which is down here and toward the back of the house, so that she could help me. And she hears me calling, and she says, Steve will be Steve. And she just didn't pay any attention. She's always thinking, I'm just being me. But I did crawl over to the side, and I had a ladder down here. After that, Packy would take care of our house in the winter when we weren't there. And I said, Packy, under no circumstances are you ever to go back onto the roof again, because you'll slip off and you just cannot go up there. He says, oh, don't worry about that. I send my nephew Jeremiah up. I said, no, Jeremiah can't go either. So that was the end of that. At any rate, so you make these panels, and they're in a series parallel connection. Which you want is, if you understand Ohm's law, You want to have the highest possible voltage you can have to have the lowest possible current, because current, power dissipation is I squared R, right? So it's the higher the current, the higher the loss. So you want to go to voltage, which is why transmission lines are 1,000,000 volts, right? Because they try to keep the current to a minimum and try to keep the voltage to a maximum, and then they bring it down to 120 volts through many steps. Well, same thing here. So that's why I didn't need that big heavy wire, and I finally figured that one out. Right? I'm an electrical engineer. It doesn't come natural. Ohm's law is very difficult. As I like to say, I think one of the lessons I learned from this is don't worry about making mistakes. There's plenty of time. Eventually you'll get to all of them. And we did. So this was our first system. It was only 400 watts, which is way too little for my house. At any rate, we created this was the control system. This is in the garage, and this is inside my house. I'm sorry. Yes, this is, oh my goodness, that was a while ago, because we moved everything into the garage except this control panel. So what you need for a solar cell system is you need what's called a maximum power point controller. So if you know the current voltage characteristic of a solar cell, it is in the fourth quadrant. You have current in the vertical axis, voltage in the horizontal axis, and you try to find the maximum product of current times voltage, which is the power. But every time a cloud goes over, it clouds the panel, and so the current goes down and the voltage comes down. So you have to track the maximum power point, which is basically taking a derivative of this curve constantly. So you need a maximum power. And of course, as the sun goes down, the current is going down, the voltage is coming. Actually, the voltage can go up even. So you always have to track that every second. So that's the maximum power point controller. Then on top of that, you need, I don't know, this is just a bunch of electrical stuff. We had to wire this whole thing up ourselves. This is going into the garage, but now this is all sitting in the garage. It doesn't look so ugly in our house. Then the other thing you need, next to the power controller, is the inverter. And this changes the DC. I think this was another thing I got wrong. We started out with a 12-volt system. What's wrong with making a system that's 12 volts? Well, you go from 12 volts to 120 volts for your house, which means the current has to be 10 times higher coming out of the batteries than is going into the house, which means you need huge fuses. Because, right? And those fuses are DC fuses. They're not so easy to find. AC fuses you can get quite easy. But you need these very large current fuses. So every time we turned on too much load in the house, the fuses would flip.
I see.
So that was another lesson of Ohm's law. And so when I converted this system, I went to a 48-volt system. And that's just a factor of, 3. A little less than 3, and so no longer any problem.
Okay.
At any rate, this changes the 12 volts in that case. Now I have a 48-volt converter to AC, and the AC now goes into the house, and we have to set up all these fuses and everything. It's pretty professionally wired. And now the other problem I have is I've got batteries. This is the old battery setup, and I have a generator. So what this thing does is, as you use the batteries when the sun is down and it's powering the house, the voltage goes down. These are just lead acid batteries, so the voltage goes down. Now you get to a certain voltage and you have no choice. The generator has to come on. So we had to create the brains. It's not too hard for an electrical engineer, that when the batteries went, and I didn't want my wife to come out and have to measure this stuff with her ohm meter and then turn on the generator. So it's all automatic. I actually it's a nice little project for undergraduates. I used the car relay as the as the thing that
It's a-
turned on the generator.
It's a basic control system.
It's a basic control system. Today, we've changed it. So this was our battery box, and it gets really cold, like minus 20 Fahrenheit there. So once my batteries even froze. So, and when they get low on charge, their pH goes up. Yeah, that's correct. The pH goes up, and they become closer to the freezing point, or the freezing point goes up too. So one day, our electrician went in the house. We had some problem. He says, "Did you know all your batteries are frozen?" And so he pulled them all out and he put them in the house and warmed them up. That's never happened since because we've done it very differently. So then once you get that all done, there it is. Now there you can see I've got 8 panels. Now I've got about 1 kilowatt of power. I wonder if, I don't show the system that I have now. The system that I have now is really spectacular. So, all right, so there's my 8 panels. It was still too little for our house. And then one day, nature fixed my problem. We live in the mountains, and we had a thunderstorm, which we have all the time, and we get microcells up there. The house was hit twice by lightning. It almost killed me. I have to tell you, but that's a longer story. It was very exciting, and after that, my wife made me wear shoes with rubber soles rather than bare feet when I tested the stuff down in the basement. But one of the things, if you look at this, this is an older version of my house. It's a metal roof. So what do you got when you got a metal roof and you got ground over here? You have a gigantic capacitor. So when the lightning hit it, it charged up this huge capacitor. And we're inside the house, and all things are going kind of wacky inside the house because the electricity system was a mess. And that's when I got shocked, and the flashlight, it was midnight when this happened. The flashlight went completely across the basement and went flying. Anyway, that's kind of the fun of having a system like this. But what it did is it fried 2 of my panels. So now I went out and I bought some new panels, much cheaper, many years later. And I'm sitting there on the ground with my son, my middle son, and he says, "All right, well, we got to get to work today and do the thing, put them back up." And he looks at me and he says, "Why don't we just put them on the ground?" Okay, that sounds like a good idea. And that's what we did. And now we have I don't show it here, a very nice 2.5 kilowatt array sitting over here behind this apple tree. So now you can't see it. We have bigger batteries. So today, our system has 2.5 kilowatts. It's plenty for the house. 1 day of sun will give us 2.5 days of operation of the house. And without ever having that generator ever come on. And it's we've got everything that every other house has. We have internet, we have dishwashers, we have, you name it, TVs, whatever any modern house has. It's not some log cabin. And it'll run for 2.5 days off of this array of 16 deep discharged lead acid batteries that sit in the garage. The only time the generator ever comes on is in the winter. Now I have to still go out and rake the snow off it. That's not a big deal because it's on the ground now. It stands about 9 feet tall, this array. But you can have 5 days of virtually no sun in the winter in Vermont. It's up in the mountains. But you can do this, and I think the real lesson here is that solar really works. And every day I'm amazed. I go out and I look at this black array of panels. It looks like glass. It's not hugely attractive, but I don't see it much. Doesn't have any whirring gears and clicking or anything else like that. Mm-hmm. The sun goes up. It gives me this electricity. I don't have to think about it. And it powers my house. It's the most wonderful form of energy you could possibly imagine. It's almost magical. The sun shines on it and I get electricity. And I don't get a bill at the end of the week or the end of the month. But I do have to replace the batteries once in a while, and I figure out how to keep the batteries living longer. They last about 7 or 8 years for the bank of batteries. So that's my only cost. And, you know, we had a Hurricane Irene basically took out everything in the state. That was in 2011. The little town of Rochester, which is 6 miles away from us, was completely cut off. And all their power was down. And my house ran, right? It didn't care because it had its own source of power.
Sure.
And of course, in Ann Arbor, our power goes down all the time.
Yeah.
It never goes down. You know, if the sun comes up, I'm good. If it doesn't come up, I'm good too.
So if you were to build a house in Ann Arbor or renovate a house, what would you combine? Would you combine solar panels with a heat pump and then buy some of
We're slowly converting
batteries
the house,
and all of that?
Well,
what would be your preferred strategy or your recommended strategy to?
Well, heat
homeowner?
pumps, we're going to be trading out our furnace for a heat pump. I think that's for sure. In terms of batteries, you don't need them here because you're connected to the grid. So it just reduces your energy bill by running the meter backwards, basically.
Okay.
So it's called, I forget what it is. It's net electricity pricing, basically. So you just save money. And if I had to build a house now, I would certainly put panels on the roof. I mean, if you go to California, they're everywhere, you know, because it's just good economics. They pay back pretty quickly because the panels cost, like I said, it's about $1 per watt retail. I'm sure you can get them for less. The power plants that go in, it's about 30 cents a watt. So, right, a 200 or 500 watt panel is going to cost you what, $150, something like that.
So you wouldn't put a battery?
Oh no, the batteries are for when you're off grid. Yeah, I mean you might want for a backup, but you know we actually in Ann Arbor we have a propane backup generator, which is for as few times as it comes on. Well, of course in Ann Arbor it comes on more than it should, but a few times it comes on, there's not much carbon load for that, and it runs our house. So like we had this big storm this winter, it was actually on for 4 days. Batteries aren't going to help you in that case because you won't have enough battery.
I see. Okay.
So here I would just run it into the grid.
Yeah.
And, you know, converting a house is slow. First thing you should do is change we had to do that with this house. He had incandescent bulbs everywhere. So
yeah, we didn't talk about lighting. That's true. So,
yeah. Well, that's another big issue and we work on it. But, you know, we started with incandescent bulbs. I took out 150 bulbs out of this house and replaced them with these miniature fluorescents, which are terrible, but they were at least, you know, they saved a lot of energy. And now I've replaced them basically with LED bulbs.
LEDs.
Yeah. And next it's going to be OLEDs. So,
Okay.
but you can see it's quite a pretty spot. It's amazing. It is amazing. And when I go there, it's like living in heaven. Vermont is just a gorgeous state. Michigan's nice too. Let's not forget. So that's solar powering my house. That was a project of love, like I said. And it still is. And we're 20 years later, and it's trouble-free. I have less problems with this house than I have with my Ann Arbor house because the systems are so much simpler.
I see.
Took us a while to get there.